Hello everyone, Zaina Ramsey here. Have you ever marveled at how robots move with such precision? It's not magic, but a fascinating blend of science and engineering. Let's uncover the secrets behind these mesmerizing movements. Robotic arms are a marvel of modern technology. Their precise movements are the result of intricate calculations and engineering. But how do they achieve such accuracy? Let's dive into the world of robotic arm movements. Forward kinematics is the key to understanding robotic movements. It calculates the end effector's position based on joint parameters. Imagine knowing exactly where a robotic hand will be just by adjusting its joints. Joint parameters play a crucial role in determining a robot's position and orientation. By adjusting angles and lengths, we can predict the exact location of the end effector. It's like solving a complex puzzle. The Danavit-Hartenberg parameters are essential for describing robot links. They use 4 parameters to define the position and orientation of each joint. This method simplifies the complex calculations involved. Consider a 2-link robotic arm. By applying transformation matrices, we can compute its end effector position. It's a step-by-step process that transforms joint parameters into precise movements. Inverse kinematics is the reverse of forward kinematics. It determines the joint parameters needed for a desired end effector position. This process is crucial for tasks requiring precise positioning. The complexity of inverse kinematics lies in its challenges. Multiple solutions and workspace limitations make it a tricky problem to solve. Yet, overcoming these challenges is key to advanced robotics. Inverse kinematics often presents multiple solutions. A single end effector position can be achieved through various joint configurations. Understanding these possibilities is vital for effective robot control. Analytical and numerical methods help solve inverse kinematics. While analytical methods work for simpler robots, numerical techniques handle complex cases. These methods ensure robots achieve desired positions efficiently. Forward and inverse kinematics are pivotal in industrial automation. They enable precise robotic movements for tasks like assembly and welding. These concepts are the backbone of modern manufacturing. Motion planning and control are real-world applications of kinematics. Robots use these principles to navigate environments and interact with objects. It's fascinating to see theory come to life in practical scenarios. Robotic software like ROS and MoveIT simplify kinematics calculations. These tools provide frameworks for implementing forward and inverse kinematics. They are indispensable for modern robotic development. Let's see inverse kinematics in action with ROS. By setting a target pose, MoveIt handles the calculations to move the robot's end effector. It's a seamless integration of software and robotics. Mastering kinematics is crucial for robotic control. By understanding forward and inverse kinematics, you enhance your robotic skills. These concepts are foundational for anyone venturing into robotics. By grasping these principles, you'll unlock new possibilities in robotics. Whether in automation or research, kinematics is your gateway to innovation. Let's continue exploring the wonders of robotics together. Recap: we have explored the magic of robot movements, delved into forward and inverse kinematics, and seen their real-world applications. These concepts are the building blocks of modern robotics. Takeaway: by mastering kinematics, you will enhance your ability to control and innovate in robotics. It's a journey of discovery that opens doors to endless possibilities. Call to action: dive deeper into robotics by experimenting with kinematics in your projects. Use tools like ROS to bring your robotic ideas to life. Let's push the boundaries of what's possible together. Thank you for joining us on this journey through the world of robotics. Stay curious, keep exploring, and let's continue to innovate in the fascinating field of robotics. See you in our next module.